Okay, so hello everyone. First of all, just a quick reminder that you can still sign up to the impromptu session. The URL is over here. Anyway, we're honored to have Andrea Montanari from Stanford as our invited speaker. Andrea did many fantastic works in machine learning, statistics, information theory, random structures, optimization, and he actually started out as a theoretical physicist. So my advisor, who is also trained as a physicist, always used to say that after you learn physics, you can pretty much work on anything. It's all easy derivatives. And I think Andrea is a good example of this. His work won numerous awards, including multiple Best Paper awards, multiple awards of the Information Theory Society, as well as the CNRS Medal for Theoretical Physics. And today he'll tell us about some fascinating topics, the intersection of statistical complexity and computational complexity and the trade-offs between them. So please, and thanks for coming.
Okay. Preliminary applauses scare me. So this is, I'm going to talk about this. So this is, let me start from something very, basic. So this is standard setting of framework for statistical estimation. We have a class of models, so these are probability distributions, and I think of them as indexed by a vector of parameters, theta. And so these are the parameters. And the classical problem is you have, samples x1, xn that are IID from a distribution in this class corresponding to a parameter theta 0. And what we want to do is estimate theta 0 from this data x1 to n. Okay? So we are familiar with this, and if you want to do some theory about this, well, you define a loss function. This should be r to the d to r to the d. So this takes the real vector and an estimate of the parameters and spits out a number, and then we try to compute the minimax risk. So this is so we try to find the estimator that achieves the smallest worst case expected loss. Okay, and this dates back more than half a century. So let me just to be make sure that we are all on the same page, give you the standard first example that everybody learned in this area, the Gaussian mean model. So here my probability distribution is the normal distribution with mean theta and covariance 1. And the loss function is the square loss, and the parameters can be any vector. So we observe data that are IID from a Gaussian mean with mean theta, and we want to estimate the mean. And okay, this is a theorem, is first theorem in this area. The minimax risk is the number of dimensions divided by the number of samples. Now, as simple as this result is really the foundation of a lot of stuff. It's really one basic reason why we do least squares, for instance, and one basic reason why we do maximum likelihood, and so on and so forth. Okay? Let me give you a more modern example. In this case, we have, again, the Gaussian mean model and lists, the square loss. So we observe, theta 0 plus noise. But now my parameter set is a little bit different. It's the set of vectors in d dimensions, but have at most S0 non-zero entries. So they are S0 sparse. This is the norm 0, the number of non-zero entries of theta. Now, this kind of problems was studied a lot in the 90s, and basically a limit case or a special case of work by Dono and Johnston in this area is that if you take, sequences of problems in which the sparsity is much smaller than the dimension, then the minimax risk has this very nice and simple form is 2S0 log d over S0 over n. And again, this is a simple, basically exact formula, and in some way was a basic inspiration to a lot of work in compressed sensing, sparse learning, and so on. Okay, so there is a tradition of computing these things very precisely. This talk will be about an obvious modification of this problem. That is what happens if my estimator is constrained to be computable by polynomial time algorithms. Okay, so here in my examples, always n will scale proportionally to d or polynomial in d, so it doesn't really matter polynomial in what polynomial will be in n or in d. And a few things that I want to, I'll try to emphasize are the following. First of all, that, basically almost every time we look at a non-trivial problem, this, polynomial time risk is much bigger than minimax risk. At least we expect. We cannot prove it often, but this is, we cannot prove it ever, strictly speaking, but this is what we expect. Second, that as in the classical setting we can come up with very precise prediction for this, we can come up with precise guesses, at least for what this is, and how these guesses are produced, involve somehow a mixture of ideas of statistics, computer science, and physics, and sometimes this suggests new algorithms. What I'll try to do is give three different perspectives on this problem. Okay? Basically what I think is that there are three different ways to look at this problem, and I'll try to give a snapshot from each of these points of view. And the flip side is that in the interest of time, each of these snapshots will have to omit a lot of detail. Okay, so for the first snapshot will be from the point of view of local algorithms. So this is a very simple class of algorithms, but they are fairly easy to analyze. The second snapshot is from the point of view of landscape, and empirical risk minimization, and the third snapshot will be from the point of view of SDP relaxation. Okay, so let me start with the first one. So I'll need an example, and my example will be the following. So this is an example that okay, it doesn't really have a name. I come up with it for this talk, but okay, let's call it a sparse low rank matrix estimation problem. Okay, so in this case, what the unknown vector, the unknown object is a vector of d dimensions, and is a binary vector, and has S0 non-zero entries. And I'm interested in estimating it in Hamming loss, right? So I want to get as many coordinates of theta correct as possible, and I'll normalize this by the number of dimensions in my formula. Okay? And what are my observations? My observations are like this. For each L, what I observe is the following: two indices, IL and JL. So these are indices between 1 and D. And then, a real numbers Y, IL, JL, and the distribution is the following. IL and JL are uniform in the index set between 1 and D. And Y is just the product of theta 0 at IL, theta 0 at JL, plus Gaussian noise. So it's a normal with mean theta 0 IL, theta 0 JL. So in a way, this is a twist, a small twist of the standard normal mean model. Normal mean model would be the same, basically, in which you observe just theta 0 IL. Here, I added this slight modification of, seeing a product, pre-processing by a product. Okay, so you can draw a picture that is like this. You have your vector, it has a few non-zero entries, and then you take two indices, you take the product of these two, and you add the Gaussian noise. Okay, let me write it in a slightly different formulation that to some of you might look more familiar, or might remind of something else, and it's the following. I can form a vector theta 0. And what I computed, I formed the matrix theta 0 transpose. This is a rank 1 matrix that I want to estimate. And I add to it Gaussian noise. So W is a Wigner matrix, so it's a matrix with symmetric, and I add the entries above the diagonal that are normal 0 sigma square. And then, I don't observe this, low rank matrix plus noise, but I observe a small subset of the entries. So I observe all the entries in a set E, where a set E has cardinality n. And this is this picture of the problem. This is the matrix theta 0 transpose. This is the matrix when I add noise, and then I sparsify it. I just look at a small subset of entries. Okay, I gave you 2 formulations of the problem. Let me give you one more formulation of the problem, and now, I hope everybody, see what this is. The third formulation is actually what I'll work with is the following. I generate a graph that is a uniformly random graph over D vertices and N edges. Okay, this is vertex set P and edge set E, and then for each edge, I can associate my variables, my unknown variables, with vertices in this graph, and for each edge in this graph, I observe theta I times theta j plus my Gaussian noise. Okay, so this is, in this formulation, this is a kind of graph structured estimation problem. So we have 3 parameters, ND and S0. It's convenient to think of the following quantities. One is the average graph degree. This is n over d. Actually, the average degree is 2n over d, so this delta is the half average graph degree. Or you can think of it as the number of observations per variable. And the other is the sparsity, that is S0 over d. And I'll be interested in asymptotics. Now one can think of 2 asymptotics. One is the dense graph asymptotics, in which n goes like d square, S0 goes like square root of d. And this is an interesting one, and is actually basically the planted click problem. What I'll discuss, because it's more convenient for what I want to say, is the sparse graph asymptotic, in which n is proportional to d and S0 is proportional to d. So in other words, delta and epsilon are 2 fixed numbers, and I look at large graph. Right? So what can we say about the estimation risk of this problem when d goes to infinity? This is the question. Now, well, of course we don't know, but okay, the first thing that we can say is the following. Okay, well, the first implication is the following. We have to look for a worst case prior, and it's not hard to see that the worst case prior is the uniform prior over all vectors of length d and support S0. Okay? This is just by symmetry, and therefore, with a small twist, we can replace this with a prior under which the theta are IID Bernoullis with bias epsilon, where epsilon is S0 over d. Okay. Okay. Now, if you look at the graph as the graph size goes to infinity, you understand very well what is the local graph structure of this graph, right? The average degree is 2 delta, right? The degree of every vertex is what? Will be approximately Poisson 2 delta, okay? And actually any vertex, so if I fix a vertex is connected to Poisson 2 delta neighbor, and any of its neighbor will have also about Poisson 2 delta neighbors, and so on and so forth. Okay, so formally you say this by saying that this graph, converges in the sense of local weak convergence to a Poisson Galton-Watson tree with average degree 2 delta. So this is just a rooted tree which has, offspring at each level Poisson 2 delta. Okay, so this is the local structure of this graph. Now, we're not interested just in the graph, right? We are interested in the graph plus the observation plus the thetas. Right? So we can attach to the graph theta on the vertices and the y's on the edges, and we get a limiting model that is a Poisson tree, in which at each vertex I generate a Bernoulli random variable with the bias epsilon, And on each edge, I put what? I put an observation generated exactly in the same way as before. Okay, so this will be theta 0i plus times theta 0j plus Gaussian noise. Okay, you can all guess what this means, that the original model locally converges to this infinite tree model. Okay? Now, once you see this, the natural hope now is the following, is that if you look at the risk for the original problem, now we have an estimation problem on a graph. The graph has a limit, as the number of dimensions goes to infinity. So what you would like to say is something of the following type, that as d goes to infinity, the risk of the graph problem coincide with the risk of the tree problem. So what is the risk of the tree problem? We are looking at Hamming loss in the graph normalized by d. So this is basically the probability that if I pick a random vertex, I estimate it incorrectly. Okay, and the natural analogous on the tree is the following. I look at the root, and what is the probability that the best estimator estimates incorrectly? The base estimator estimates incorrectly the root t. Okay, so the question is this equal to that? Okay, now is where things starts getting a little bit interesting, because we have to be a little bit careful about how we define this object on the right hand side, because y is an infinite set of random variables, right? So just to be very concrete, let me do the following. You can think of taking this infinite tree and looking only at the vertices or edges that have distance at most L from the root, for some fixed constant. So a bounded neighborhood of the root. And then you can look at the estimator that uses only this information. So what is the optimal estimator that uses all that information? You look just at the posterior of the root variables, given all the variables between 0 and L, and then you maximize the posterior. This is the base optimal estimator given that information. Okay? And then I define this object, R lock. This is the limit as L goes to infinity of the estimation error for this model, okay, where I use all the information up to L. Okay? So why I would call this a local risk? Well, if I think about it, any such function theta hat give me an algorithm that I can implement on a graph, on a finite graph over the vertices. Simply for each vertex, I look at the ball and radius L around that vertex and apply that function. It's obviously a polynomial time algorithm. Actually, it's a linear time algorithm because I do a constant number of operations per each vertex. Okay, so this is then I take the limit as L goes to infinity of this. This will be the optimal risk that I can achieve by any local algorithm, right? Because given the distance L, what I'm doing the base optimal thing, right? So R lock is really the risk in the d infinity limit, the optimal risk that can be achieved by any local algorithm. Okay? In fact, this is a connection with things that people do in practice in graphical model. Actually, this is the risk that is achieved by standard algorithm for inference in graphical model that is called belief propagation, right? So what is belief propagation? It's basically doing the following: looking at each vertex, looking at a ball around that vertex of some constant radius, and doing base optimal estimation in that ball. The only twist on this is that since that ball is with high probability, a tree, what belief propagation does is, instead of doing base optimal inference in the silly way, it uses dynamic programming for doing in time that is proportional to the ball size and not exponential in the ball size. Okay, so this is something that you can achieve really with small complexity. Now, one other interesting thing is that you can compute what this risk is, and the reason that you can compute it, or you can say things about it, is that basically once you reduce to a tree, then you have the recursive structure of the tree that allows you to do a lot of computations. Okay, so this is for my example. I fix epsilon 0.02, so you have 2% of vertices that are special, and noise 1.5, and then I computed this local risk, and this is what it looks like. It is very bad up to some threshold, and the threshold, very bad meaning it's essentially 0.02, so basically I'm missing all the vertices, and then, okay, so this is actually, and then it starts dropping. Okay, and actually it has a discontinuity. Okay, so this is the local risk. Okay, so in fact you can not only compute it, numerically, so this is the numerical computational trick, but you can say things about this. So this is an adaptation for a theorem that we proved in a slightly different model. So in our model we had Bernoulli noise, but what we proved that this kind of local risk has a phase transition when the number of the degree of the graph of the number of samples per dimension is of order sigma square over 2e epsilon square. Okay? So there is a sharp threshold in this parameter. Okay. Now, this gives one possible definition of the limit. Another possible definition of the limit is the following. I look at all observed variable in a ball of radius L around my root. And then I also give you all the labels, the unknown variables, at distance below L. Okay? So this is kind of, a problem in which you have much more information. You don't have only the y's, but you have the theta's, but you have the theta's only far away. Okay? And again, I define the theta hat given this enhanced information as the base optimal estimator given that information. And this allows you to define a kind of oracle risk. This is the probability that you'll guess the root wrong given this additional information. And okay, here there is a key typo. This is plus. Okay. Okay. As in the previous case, it turns out that you can compute it. And what does it look like? Again, it's very, very bad about up to a certain threshold. And the threshold is here. And then starts dropping. But above the local threshold, it coincides with the previous one. Okay? Now, something interesting in this case is that, quite clearly, for all possible estimators, the risk will be between the asymptotic risk will be between the oracle risk and the local algorithm risk. Okay? So the local algorithm risk can be achieved by local algorithms, and this is a risk that you achieve the optimal risk under additional information, so it's a lower bound to anything. So any algorithm must stay in this small region here and coincide with these two above here and coincide with these two above here. Okay, so I guess the first point that I want to emphasize is that these two things are fairly easy to compute or fairly easy to characterize, and quite often what happens in practice is that you see this gap between these two. And this gap between the two is really the hallmark of problems that are statistically hard, statistically doable but computationally hard. Okay, so you can do analysis for this oracle. For the optimal risk of this problem, and okay, this is again adapted from a result on a slightly different model, but what you get is that this is a phase transition, but the phase transition is at sigma square over 2 epsilon log over 1 over epsilon. Okay? So this result, in the case of dense graph, people obtained, sharper result. In particular, there is a paper, I guess tomorrow that is related to this problem. But the interesting point is that in this and in a large class of kind of closely related problems, we don't have any algorithm that works between what is the local algorithm threshold and something very close to actually the oracle threshold. If you find where the statistical threshold is actually very close to the oracle threshold. Okay? So this is a phenomenon that comes over and over again and is correctly predicted by these two very simple calculations. Okay, so this model and similar model brings up a few obvious questions, and the basic questions are, can we beat this local algorithm risk by anything else that is polynomial? Obvious candidates are Gibbs sampling and convex relaxations, right? I don't know of any case in this class of examples in which you can prove anything better, obtain better results than local algorithm by other methods. And the real lurking question here is the polynomial time risk equal to the local algorithm risk? And this is actually what is normally conjectured by statistical physicists, that basically polynomial time algorithm can beat local algorithm, cannot beat local algorithm, except possibly for cases in which a small amount of side information helps you change the threshold. Okay, so one peculiar thing, one feature of this problem is the following. So let me add something. One feature of this problem is the following. Suppose that I take the same problem and I reveal labels of a sublinear fraction of the vertices. Turns out that this doesn't change the local algorithm curve. Okay, so the full conjecture that comes from physics is basically that this local algorithm aided by small genie cannot be beaten by any polynomial time algorithm. Okay, so now I described this in a very special problem, but this phenomenon is kind of ubiquitous. Okay, and it comes up always with the same phenomenology. Okay, and the phenomenology is the following: you compute the risk for local algorithm, you compute it for the oracle, and you get a gap, and the one for local algorithm is also the same as local algorithm plus a small genie. Okay, David.
Local algorithm, do you really mean like constant depth or logarithmic depth?
Constant depth.
Because I thought for some community detection type problems, if you only look at constant depth, you can't really do anything.
Yeah. Yeah, so this is why I spoke about the genie, and this is why I chose so first of all, so the real conjecture is that you should look at the local algorithm plus the genie.
Is that like the oracle? Oracle?
Yeah, and no, the genie reveals you sublinear number of edges of vertices. Okay, so I choose in particular here a model in which the genie plays no effect, because what happens is that there is a bias. So just by guessing, you always can do better than the trivial estimator by guessing in the right direction. So there is a bias, so there is not an unbiased fixed point. Okay? So this is like the community detection problem in which there is slightly different degree in the two communities, right? So the degree gives you a little bit of starting point. So basically what happens is that the genie doesn't help you more than that. Okay? Okay. So, but, I chose this example exactly because I didn't want to go in the genie question, but, the real picture as the genie side. Okay? So this is ubiquitous. This problem is that I described is kind of peculiar. Seems to be a little bit of a made-up problem, but the same phenomenology emerges pretty much in any, in a lot of the statistical estimation problems that have a lot of symmetry and exchangeability. One example is, for instance, sparse principal component analysis. This is the problem of estimating a low-rank sparse matrix, UV transpose plus noise, where V is sparse, right? Okay, so basically the same calculations can be done in that case, and they show the same gap. Of course, the hidden click problem is closely related. The community detection problem, this is the problem in which you have, K, n d vertices and d over k vertices in each communities, and edges within each community with some probability and without with some other probability. Again, you can compute this local algorithm threshold and oracle threshold, and then diverge. And finally, one that I'll discuss a little bit next will be tensor principal component analysis. Okay, so this gives one way of looking at what problems are hard and what problems are not hard. Another possible way is looking at landscape of empirical risk minimization. Okay, so what is the setting here? Again, we have a class of models, and then we have IID samples from one of these models, and the way we look at this now is we try to minimize a risk. Okay, so we try to minimize a loss, so this is the sum of L theta xi. Okay, and of course the rationale for this is that the real parameters that we want to compute is the minimizer of the population risk, which is the expectation of this empirical risk. Okay, and I want to talk briefly about two things. First thing is what do we know generically about this minimization problem, and second, how does complexity show up from this perspective? Right. So what can we say generically? Well, one thing that we can say generically is that the empirical risk is close to the population risk when the sample size is big enough, is uniformly close over all the parameter set. And okay, here one can be very sophisticated about what this star is, but I think of it as just the dimension or the number of parameters. Okay. So this is the picture. We have the population risk, that is some nice thing that has a global optimum at the parameters that I want to estimate, and then we have the empirical risk that is in a narrow band around the empirical risk. Okay, now if you plot this, so this has of course a lot of implication. In particular, it implies that your M estimator, your minimizer of the empirical risk, is close to the minimizer of the population risk. For instance, is close in the loss, in the prediction error. Of course, if you plot a figure like this, the natural reaction is okay. Will I be able to minimize the empirical risk? Looks like there can be, in principle, a lot of local minimum, so this can be a little, much more complex than this object. Okay, so landscape analysis is about analyzing, basically the structure of this landscape. Okay, so this is a very simple result in this direction. So the assumption that I'm going to make is the following: that my set of parameters is a ball, is an L2 ball of some radius r. The data are IIDs, of course, from some distribution, and the gradient of the loss that I'm minimizing is tau square sub Gaussian. The Hessian, when you sandwich the Hessian between two unit vectors, you get something that is sub-exponential. And finally, two things that are quite mild. One is that the function is the Hessian is bounded at one point, say at 0. And the second is that it's a Lipschitz continuous function with a Lipschitz constant that is polynomial in the dimension. And here is also bounded by polynomial in the dimension. Okay? Okay, so these assumptions are not really mild, but this is what makes things kind of doable. And okay, so this is a simple lemma in this direction. Under this assumption, if you give me a number of samples that is a little bit bigger than this should be d log d, then the following holds. The gradient of the empirical risk is uniformly close to the gradient of the population risk, and this close means if of order square root of d over n modulo log factors. And second, the gradient of the Hessian is also close to the Hessian of the population risk is in operator norm. Again, close means that the optimal rate should be square root of d over n, and there is this log n factor that is possibly spurious. Right? So this tells you the following, that what happens when you go from population risk and empirical risk. This cannot happen because this is a case in which r hat is close to r, but the gradient is not close to the gradient. And instead, things must be this must look like this. Okay. In other words, if you have a nice population risk, you have a nice empirical risk, and in particular, minimizers of these are close to minimizers. Local minimizers of this will be close to local minimizers of this object. Now, one can formalize this in a number of ways, but let me just give one example. One example that I'll give is binary classification. I have data that are yi xi, where yi is a label, it's a binary label, and xi is a feature vectors, and they are generated according to this model. So the probability that yi is one given xi is just some sigmoid function applied to xi, to sigmoid function applied to theta 0 times xi, and now the way I learned this model is I minimize this risk. That is, you can think of it as a smooth version of the 0-1 loss, in which I minimize the sum of squares error. Okay, yi minus theta of sigma of theta times xi. No? So this dates back to the very first works on the perceptron, and of course has many extensions. And okay, so one possible motivation for this loss, instead of logistic or support vector machine or hinge loss, is that is bounded. So you expect it to be a little bit more robust to outliers. Okay, so suppose that I try to minimize this loss. What happens? Well, what we can prove using that lemma is the following, is that if these xi's are center sub-Gaussian and they span the whole space, meaning that the covariance matrix is lower bounded by some delta, and if this function sigma is nice, namely has 3 bounded derivatives, then the population risk has a unique critical point. So it doesn't happen that there are multiple local minimum. There is a unique local minimum, and this is the global minimum. And then if you run gradient descent from basically any initialization within this ball, you converge to the global optimum. Actually, you converge exponentially fast to local optimum. And third, that the minimizer of the empirical risk is very close to the minimizer of population risk, and very close means square root of d over n, that is the parametric rate up to this logarithmic factor. Okay, and this logarithmic factor is an effect of this that logarithmic factor in the uniform convergence problem, and possibly can be improved. Okay? So this is an example application in which very concretely I show this philosophy of analyzing the population risk and then transferring the feature of the population risk to empirical risk using this small lemma, and we have in the paper a bunch of other examples to, like non-convex robust regression, 1-bit compressed sensing, etc. Yeah. Oh, yeah, that's empirical. Thank you. Thank you. Right, so I put a few typos at crucial important points to check that Amin is following. But Amin is following. Okay, so this is part of a growing literature within theoretical statistics using non-convex losses. Okay, so we are not the first looking at these problems. Pauline Low and Martin Wainwright had a series of papers in which basically they prove convergence to what they call statistical neighborhood. So they don't show that there are multiple local minima. They don't show that there exists a unique local minimum. That they show that there are possibly multiple ones, but all sufficiently close to the global one, to the population risk, which is a nice result. But okay. It's a nice result. There is a bunch of other results that basically what they do is they don't prove that there exists a unique one, but they prove that if you find a way to initialize well, and typically this comes from some spectral method, then you converge to the global optimum. This is also nice, but unfortunately, but in practice people don't use this spectral initialization. So you would like to have a theory that also doesn't use spectral initialization. And then there is a relatively small set of papers that prove the same kind of feature, a unique local minimum. In the case of regression, there is a result by Pauline Low, but okay, it has the wrong scaling. In the case of phase retrieval, Stephen Wright and co-authors, and the case of matrix completion, Jelly and Ma. So these are things that we can say generically. Now, I'm a kind of pessimistic person, so I'm always interested in what can go wrong. So what goes wrong about this story? Well, you understand, if you understood the lemma, you understand it very easily. If the population risk is very flat, then the empirical risk can have many local minima. Okay? And interestingly, in some example, this is surprisingly close to this threshold when local algorithms fail. Okay? So my favorite example of this is this spiked tensor model, because it's probably the simplest example. Here the parameter vectors is a unit vectors in, say, n dimensions, and the data is what? Is theta 0 tensor k plus w, where w is a Gaussian noise tensors that, let's say, is symmetric. So what does this mean? It means that, okay, what I observe is a table that is n by n by n by n, say in case k equals 4, and the noise is also a table n by n by n that is filled with IID Gaussian entries that up to symmetries. Okay, and these are normal 0, 1 over n. Right, so this is in coordinates. Okay, so what we know about this problem? Okay, so this theorem puts together, for brevity, some easy results that were proved by myself and Emile Richard, and some harder results that were proved by David Stoirer and co-authors, Sam Hopkins and Xi. And the picture goes as follows. So this problem is parameterized by one number lambda. This is an integer that gives you basically the strength of the signal. It's the signal to noise ratio, right? So this is okay, I should have said, but this is a natural generalization again of something that is very classical in statistics. That is the spike matrix model that was studied by many people, but in particular by Ian Johnston and Liu. So this is a natural generalization of that. Now, the problem, of course, becomes easier when lambda is large. When lambda is large, the signal is very strong and the problem is easier. Okay? So now you want to figure out what happens with it. First question is, first statement is the following. There exists a constant, call it lambda ml, such that if lambda is bigger than the constant, and if you compute the maximum likelihood estimator, so, okay, I'll write in a slide what the maximum likelihood estimator is, but you can probably guess, then this is, as a strong scalar product with the true vector, with high probability, okay? So I simply do the obvious thing, maximum likelihood estimator, if lambda is bigger than some constant, maximum likelihood is very close to the truth. Second statement, if lambda is smaller than some other constant, then no estimator will achieve a positive scalar product. Okay? So if lambda is smaller than something, any estimator, this is a statistical result, any estimator will be basically orthogonal to the true vector. Now the interesting fact is that the best polynomial estimator that we know achieves a large scalar product only if lambda is at least n to the k minus 2 over 4. Okay? So for k equal 2, that is the classical case, this is a gain of order 1, and indeed it is easy to see that the three thresholds exactly coincide, and they are equal to lambda equal 1. So in that case there is a phase transition at lambda equal 1, and below that phase transition no algorithm gave a positive scalar product, and above that there are polynomial time algorithms doing. In fact, spectral method does it. In this case, there is a huge gap between the two. So this is basically pretty much the same phenomenon that I described in my first example. There is this intermediate phase in SNR in which polynomial time algorithms don't work, but other non-polynomial method works. Okay, and okay, I cited this result. In fact, there are much more accurate results. In particular, the exact threshold for statistical estimators has been computed in this paper. Okay, and this is something that shows up in practice. This is if you run this problem, these are 6 different algorithms that we tried, and this is the scalar product theta 0 times theta as a function of the SNR. Okay, here it's called beta instead of lambda, and what happens is that as the problem size increasing, the probability of success drops to 0 for any constant beta. So there is at small beta there is a threshold, at small n there is a threshold at some finite beta, but this threshold moves to the right, and the theorem predicts that the way it moves to the right, so this is k equal 3, it moves to the right at a speed that is n to the 1/4. Okay, so can we understand, one interesting thing is that we can understand this fairly easy, that this is going to happen by looking at the landscape of this problem. So what is the maximum likelihood estimator? Is just minimizing the following, minimizing y minus lambda theta tensor k over the unit sphere. Okay, once you expand the square, this is equivalent basically to maximize y times theta tensor k. Okay, so we are maximizing a polynomial of order k over the unit sphere, and the coefficient of this polynomial are given by our data. Okay, so maximum likelihood is minimizing this. Okay, so this is our empirical risk in this problem. What is the population risk? The population risk is the expectation of this object, right? Now, if you take the expectation of y, remember y is theta 0 tensor k plus noise. So if you take the expectation of y, you can get theta 0 tensor k. So you get the population risk that is theta 0 times theta to the power k. Okay, and now what I'm going to do is a very quick back-of-the-envelope calculation, and the back-of-the-envelope calculation is the following. Suppose that I started a random initialization, and I run gradient descent. Will the gradient point me in the right direction? Okay? The guess is that if the gradient doesn't point me in the right direction at all, probably I will fail, right? So what is the gradient of the population risk? Of course, it points in the right direction, but has this coefficient in front that is due to the fact that the population risk is very flat here. Okay? Now, if you start with a random initialization, the scalar product is n to the minus 1/2 typically. So if you look at the fraction of the gradient that points the gradient in the direction of the ground truth in the right direction, you get the scalar product to the power k minus 1, and this is n to the minus k minus 1 over 2. So this is the expected drift in the right direction. And then there are the fluctuations due to the noise. And if you compute this, it's very easy to check that this is of order n to the minus 1/2. Okay? So this will point in the right direction when this guy beats that guy. And this happens only if lambda is bigger than n to k minus 2 over 2. Okay? So this is kind of, it's a very simple calculation, but kind of predicts where the problem comes from. One can try to do more complicated calculations, or something that we did recently is computing the number of local minima of this problem. Okay? You have this complex function over the unit sphere. This has a lot of local minima we expect. Can we compute their number? So what we did is that we computed the expected number of local minima that have a scalar product with a ground truth that is m. So this is how close we are to the ground truth, and they have a cost function that is x. Right? And this is I will not give formula, so it turns out that this number, local minima, is exponential in the dimension. So there is a humongous number of local minima, and okay, at least in expectation. And they look like this. There is a region in this place in which this exponent is positive, and this is the region depicted for k equal 3 and lambda equal 3. And this is the exponent, how it looks like, so it's positive in some interval around m equals 0. Okay? So there is an exponential number of local minima, and most of them are basically completely uncorrelated with what you're interested in. So this is exactly the opposite picture than you would have in the kind of statistical neighborhood problems. Most local minima don't have anything to do with the truth. Okay, so I want to quickly, perhaps in 5 minutes, talk of this last point of view. So I'll be quick also because there is I saw a couple of talks about this topic, I guess tomorrow. One thing that is very interesting, so of course SDP hierarchies, SDP relaxations are among the most powerful set of algorithmic tools that we have. Something that is really intriguing is that in several of these random statistical estimation problem, the following happens. I started by describing a very simple set of algorithms, that is local algorithms, and I said at some point they fail. Okay, and you might say, okay, who cares? These are very silly algorithms, they fail because of that. But in many of these statistical estimation problems, if this algorithm fails, even SDP relaxation fails. Okay, this is kind of surprising, especially if you come from a computer science perspective. And one question is why? Okay? And one explanation that I like, one possible explanation, is not an explanation because we don't have a theorem, but one possible intuition is that perhaps what happens is that on some instances, on this kind of instances, you can solve SDPs by local algorithm. If that was true, then this would imply this collapsing of the hierarchies, because we say that one is as powerful as the other. Okay? So we cannot prove anything as strong as that, but we can prove something in a very specific problem, and this is the following. SDP. So I'll give it to you with very small justification. You have a graph G. I construct out of the graph the centered adjacency matrix. So this is the adjacency, the matrix that has entry 1 minus d over n for d at the average degree if ij is an edge, and minus d over n otherwise. So it's basically the adjacency matrix in which I subtract a constant in such a way to make it zero mean. And then I maximize, I solve this standard and max cut SDPs, in which I maximize A times x over the elliptope over x PSD with diagonal entries equal to 1. Okay, of course, I will not go into trying to justify this, but this SDP appears in all sorts of problems, in graph clustering, in graph embedding, and in community detections, and so on. Okay, so the question that we asked ourselves is, can we solve this SDP by using a local algorithm, at least on a random graph? Okay, so what I mean by solving it by a local algorithm, I'm given a graph, and now I want to come up with an SDP solution. How do I do it? I'll do it in the following way. For each vertex in the graph, I'll generate a random standard Gaussian entries. So a Zi that is normal 0, 1, and then at each vertex I compute a function of a neighborhood of that vertex. So I apply some function f to the neighborhood of that vertex and to z restricted to that neighborhood. So I look at a ball about my vertex v, and then I merge all the information in that neighborhood using a function, some function f. Okay? Now this gives me a random vector indexed by the vertices of my graph, and what I output as an SDP solution is just the covariance of this random vector. And I have to correct it a little bit for other reasons to make it balanced, but okay, basically I output the covariance of this. And the question is, okay, so this is a very simple algorithm, it's a linear time algorithm to solve a semi-definite program. Can this achieve the SDP value? Okay? So I think this is a very interesting question. As a matter of fact, it's still open, but we can prove the following, that if you look at the SDP value, it's bounded by something like 2 square root of d times 1 minus 2 over d, and local algorithm can achieve something that is fairly close to it, is 2 square root of d times 1 over d plus 1. Okay? So, in particular, this is, they match each other for large d, and for any value of d, the upper bound and lower bound are within a factor 9 over 8. Alright, so this is how it looks like. This is the SDP values. So this is the SDP values for a random Erdős-Rényi graph divided by the asymptotic large degree prediction, that is 2n square root of d. The dots are simulations, so this is what you get if you solve a SDP on a large Erdős-Rényi graph. I think this was something like 10,000 nodes. Okay, so asymptotically it goes to 1, but is fairly different from 1 already at d equal 8, and this is the lower bound that we can achieve by local algorithm, and this is an upper bound. So they are very close. So we cannot prove that you can solve this SDP on Erdős-Rényi random graph, but we can almost solve it. And in fact, we have a better algorithm that I don't describe here, a better local algorithm that achieves this second curve. The reason I don't describe is that there is not such a neat formula for this second curve, but it's basically pretty close to what you get in simulations, and actually so close that is above the numerical values. So it's a lower bound that is so good that it beats the true value. Okay, so I think time is over. Yeah, so I tried to describe this point of view, and one thing that I omitted is showing that in many of these cases, the point at which this various class of algorithm fails is pretty much the same. So I think that this brings quite convincing evidence to this kind of prediction to be really an indication of real complexity. All right. That's all. Thank you.
So yesterday morning there was actually another talk by your student Song Mei about solving SDPs, but like in a somewhat different setting where you take this low rank approach. So can you comment maybe on connections between this and what you talked about, similarity in techniques, or is it totally different?
The technique is very different. So one thing that is similar is that somehow we don't get, in this paper we don't get what something that captures what really happens in practice, right? So in practice, so I started getting interested in that for the same reason, right? So I had to solve SDPs for this community detection problem, and I had to solve the large SDPs. So the way I did it is that I did the low rank formulation, and then at each step I would pick one vertex and do optimize with respect to that vertex, right? So take the vector that maximizes the cost function, in that thing, right? So now if you run that algorithm works very quickly and seems to be almost linear complexity, okay? Again, for the community detection instances. Now, if you think about it, this is basically very close to a local algorithm, right? Because at each time I update only one variable at one vertex. So in linear time, I will explore only, almost a linear neighborhood, perhaps a little bit above linear of my vertex. So again, I think that if one did a very good analysis of that algorithm, perhaps one could prove that you can solve SDP by local algorithm here, right? So that, somehow I had the common motivation for both of the results, but they both then kind of diverged.
Okay. Yes, one more question.
So you focused on local algorithms. What about temperature-based algorithms? Just give me a high-level intuition. What do you think of those? And adding noise to get out of local minima.
Right. So okay. Many of these problems you can define. You can look at temperature-based. I guess means something like Gibbs sampling, right? Yeah. So I don't know of any sharp analysis of this and this. Of course, there is kind of results like Jerome 92 paper on the planted click problem, etc. But they are not as sharp. But the guess and the intuition again that comes from physics is that the phase transition at which those methods start failing is exactly the same as local algorithm. And one high-level reason why that should happen is that somehow there is this general connection between spatial mixing and temporal mixing, right? So if things mix in space, then they mix in time, and vice versa, right? So this is a general connection and an old connection in Markov chains. So somehow local algorithm working is pretty much related to spatial mixing, and Gibbs sampling working is pretty much related to temporal mixing. Now the thing is that the twist is that here we are not interested in mixing with respect to worst case instances or worst case initialization, but we are interested in typically in random initialization, but the connection should be there. For instance, one thing so that is one connection. One other connection goes to the landscape picture. So in these problems where there is many local minima, what also one can show typically is that these local minima are not shallow, but they have linear depth. So if you get into one of them, it takes exponential time to get out of them. So when these many local minima appear, not only descent algorithms will fail, but also, Markov chain algorithms will fail.
But you compare them in terms of bounds. Did you do experimental comparison?
Experimental comparison. Okay, yeah. So let me see which problems did I do experimental. So for instance, on this problem. Okay, so there is something that is this problem without the spike, so without the signal. So that problem has been studied extensively in physics. It's known as the P-spin model. And people, simulated, and they have a whole theory of how Gibbs sampling works, and basically what it does, it gets stuck at what are called the threshold states. So this is my energy that I'm trying to optimize. So I start with a random initialization. So basically I start with 0, and then I try to maximize energy, and if I do Gibbs sampling, I get stuck here. So I get stuck at the highest local minima. Okay, so basically you do get the same as if you do whatever gradient descent or proxy other descent methods. So, and there are a bunch of other problems of that type. For instance, if you look at Gibbs measures on sparse graphs in which the same coincidence comes up. So on one hand, you can compute, this kind of dynamic, this kind of thresholds that corresponds in my language to this local algorithm threshold, and then you can simulate Monte Carlo, and this seems to be failing at the same threshold. But so there is evidence coming from those studies that shows that the two are very closely related, and there is evidence coming from theory, but nobody has done really careful analytical study of this.
Very good, thank you.
I think maybe in the interest of time we'll take further questions offline. So let's thank the speaker again. And since we're running late, we're going to resume the next session at 2:50. So that's 10 minutes before 3.